Okay, good afternoon, all. Welcome to this next session. In this session, we'll be talking about how to handle imbalanced data sets. Now, most of us, as part of our data analytics journey, we would have worked with textbook problems where the data is typically nicely balanced, the machine learning algorithms work fine, you get nice results. But in real life, more often than not, you'll be faced with challenges where the data is imbalanced, sometimes really highly imbalanced. For example, say you're trying to predict frauds. Now, a fraudulent transaction may be one in a lakh or maybe one in a million. So how do you work with such problems is going to be the topic of this discussion. Now, in terms of introductions, my name is Amit. I have around 14 years of experience, and I'm currently working with Thoucentric as a data scientist. I'll be the moderator for this event, and let's try and keep the session as interactive as possible. So request you all to please send in your questions, and we'll try our level best to address all your queries. In this webinar, we also have some audience questions. So when prompted for those questions, request you all to please key in your responses, and let's keep it as informative and as interactive as possible. Now, let me introduce the speaker for this session. I would introduce Swati Gupta. So Swati is an IIT Kanpur alumnus, and she has over 17 years of industry experience. She has worked in a wide plethora of analytics domains, right from CPG to retail banking, consumer finance, predictive quality and maintenance, digital marketing, supply chain analytics, I mean, whatnot. And she is also the co-lead for the analytics and machine learning practice at Thoucentric. She's one of the most senior members of our team, and it's my privilege and pleasure to introduce her to start this webinar. Swati, all over to you.
Thanks a lot, Amit. Thanks for that warm introduction. Please let me know if I am visible along with the slides.
Yes, you are.
All right, great. You know, the task that has been given to Amit and I is especially challenging because we're just out of this interesting panel. Right, and we don't have the luxury to say that you know, the alertness levels will be down because we're just after lunch. No, we are neatly sandwiched between two very interesting sessions. We don't have the luxury even to say that, you know, hang on, guys. You know, we're the only ones between you and the day end. Right, so please hang in there. We'll try to make it as interesting as possible for all of you. That said, what I'd like to do is begin with this micro story, just to set the context. So this one is about John Doe. He is someone who's just collapsed, unfortunately, in an ICU room. And what has happened is that he was on a morphine pump, which has had a rare malfunction. Right, so the investigating doctor, Dr. Lena and Tom, they are debating what really happened. Right, so what has happened is that the pump, which was programmed using a machine learning algorithm, has injected a wrong amount, a profusely high amount of morphine into his body. You know, the machine learning algorithm has malfunctioned. Right now, the point is what really happened. It may be 1 in a million thing, a really rare incident, but has taken somebody's life. Right, so. This machine learning algorithm, which was used to, you know, calculate the amount of morphine to be injected, runs on, you know, by using the sensory inputs of the patient, and some rare combination of these inputs has caused it to malfunction. Now, you know, again, the point is, a lot of you here, I'm hoping, are ML practitioners. So maybe you'd like to think and hypothesize on what could have gone wrong. From an ML perspective, what could have really gone wrong here? As Amit said, we'd really encourage you to sort of keep typing in your comments here, maybe the hypothesis in this case. All right, so maybe you don't have questions, but we will have few as we move on, and with the flow, we'll try to integrate your questions and your thoughts into the discussion. So the few initial questions maybe around, you know, what are really your expectations? A lot of you may have handled such challenges in your careers, right? Such projects in your experience. So what really you expect is something we would like to listen and answer as we move on.
Right. To all the participants, please feel free to send in your questions. Oh, okay, excellent. We have one interesting question here. So this person, the name is anonymous, but he asks, how do we know that my data is imbalanced? Is there a benchmark which says,
Right.
Swati, would you like to take this up?
Yes, sure. Amit, I think we have a slide which sort of answers this question later on. And let me, if everybody's fine, we'll just pick it up probably at that slide. It'll rhyme and well.
Sure, sure.
Fine. Yeah. So before that, right, we would want to just take few examples, because although this imbalanced data situation is very, very rare, it's not very impractical to find. Most of the real life cases that you encounter, and Amit had alluded to one right at the beginning of the session, fraud, for example, right? In finance, fraud is something you all might have heard. Pretty popular use case, has been researched upon and studied maybe for the last 20 years or more, right? If you look at 2018 and more recently 2020 figures, the total losses that can be attributed to fraud totally on the payment side of things may be reaching to about 30 billion US dollars. Pretty huge in terms of its impact, and hugely studied. Right, we have three more use cases here. Pretty close to our heart is other use cases in production domain. In manufacturing, we are working on quite a few projects, as we talk in this particular space. Right, what you see here, we've highlighted one of them coming from the paper industry. Web breaks, right? As the paper rolls are being manufactured, there is this rare event of the roll breaking, right? And in terms of losses, close to $5 billion per annum, or maybe more now, right? So again, a rare event, but very complicated and hugely studied. Medical, all of us again know about cancer detection cases. Breast cancer, one of the most frequent cancers amongst women, but a complicated study from ML perspective. Again, because the number of cases and the complications in feature extraction in this particular subject. Again, the last one is pretty close. We've discussed this particular issue all through our webinar. So COVID-19, right? If you look at any of the rates that have been talked about with respect to this pandemic, all of them are sub maybe 10%. Right? So again, a rare event, difficult to understand the implications, nevertheless, very, very critical for studies. All right, so few more examples here, but really the point we're trying to make is that be it medicines, be it biomedics, talk about computer vision, umpteen number of examples from the industry where we were trying to investigate this open challenge of handling imbalanced data. All right. So coming to the question that I think somebody in the audience has asked, how do we define class imbalance really, right? So this, in fact, is one of the biggest confusions as any practitioner starts in this field, begins in this field, and no hiding the fact that when we started, and Amit and I have been recently working on this project as well. When we all also started, we were also trying to draw the line of, when do we call this data balanced, and when can we just use the standard machine learning techniques. Right, so the answer is not very straightforward, right? If you and I'll probably use my pointer options here. Okay, so I have borrowed this definition from a very popular book on imbalanced learning, and I will give the book credits as we move on. But really, if you look at the definition here, a data set is said to be imbalanced when there is a significant or in some cases extreme disproportion amongst the number of examples. So as long as the ratio of minority to majority class or the positives to negatives, whichever way you want to call it, is not 1:1, we can call it imbalanced data set. But really what matters is the degree in terms of the disbalance that you're seeing. Okay, so if it is not 1:1, it is imbalanced. If the ratio increases, and I will use this term very often, the IR ratio, the imbalance ratio, which really is the ratio of negatives to positives in the data set that you are analyzing. So if this ratio is more towards, let's say, 4 or more, we typically would suggest using any imbalanced machine learning algorithm. Okay. So I hope that answers the question, Amit, that we had in the audience chat.
Right.
Do let me know as we're moving on, and if you feel there's any pertinent question to the topic, let us keep answering those as we move along.
Right. There are a few more questions, but I think we'll take it as we go along at the relevant sections.
Right? Yep. Okay. Oh, we have one. So as I said, if you don't ask questions, we will have tons of them for the audience. So the question that we had was really what kind of imbalanced data problems have you encountered, which has drawn you to this talk? If at all there's something specific that you have in mind, please do keep typing in terms of your challenges. Could be around the data set that you're looking at, could be around the machine learning algorithms, or maybe just simple things like feature selection. Okay, so as I was saying, we have in the study borrowed a lot from the research that has been done in this space. In particular, these are the 3 studies that we have extensively gone through. I would not say end-to-end because these are really huge books. But there is this very recent publication, which is in the form of ebook from Jason Brownlee, which talks about how to handle such data sets using Python libraries. So very, very useful book, as such. Then there are a few others. One Wiley publication from Haibo Hay, Imbalanced Learning, and another very, very famous 2018 publication from Spring. So I hugely recommend for people who are really working in this space to sort of go through these. All right, with those credits done, we will delve into the subject. The way I'd like to take up this whole talk is organize it in this framework. We would like to take a binary classification example. This is an area where we've done extensive work in the last maybe 6 to 8 months. So we try and stay focused and demonstrate through this example. All right, so these are the 2 studies that we will use along as a part of the demonstration of the whole framework. One is, and I was referring to this earlier as well, this is the C case. We'll call it as a C case through the presentation. This is a very popular data set called Wood's mammography data set. It has basically mammograms for few cancerous patients and few healthy patients. Again, breast cancer is the topic of the study. This is not very hugely imbalanced data set, just about a 2% in terms of the cancerous or positives. 11K records roughly, the IR ratio is 42. We would try and contrast it with another data set that we have been using for the study, which is in the area of manufacturing. As I said, defect detection is one of the key areas of study in production and manufacturing domain. We would call this data set as the D data set. Again, pretty similar if you see in terms of number of positives and IR ratio. Right, but you would see as we move on, the difficulties and the challenges are very contrasting, right? So what we would really do throughout the framework is answer these 3 questions. What is the right metric, right? Given the 2% positive rate, is 98% accuracy really good enough, right, for the model that you develop? If not, then what is a good metric to be used? If you have, let's say, 15, 20 models developed, how do you assess and compare these models? And then finally, we would also try to give you a way out of this whole maze of, so many machine learning algorithms, some specifically for standard, classification, and some very, very specific algorithms for imbalance cases. All right. Yeah. Okay, so this is the framework that we would suggest for anybody who's working in this particular space, and pretty standard, I would say, barring few nuances which are associated with the imbalance classification. So we would start with defining the problem, understanding the data set very, very deeply, right? Because a lot of cases you would find that skew is not the real problem. The real problem lies somewhere else. So we begin with that. And then we would look at what are the various evaluation metrics available for such cases, beyond accuracy, obviously. And then we would look at what are the classifiers available, to do such binary classification. Are there any balancing methods in order to artificially balance the data set before using any machine learning algorithm? And lastly, we would summarize it up with how to fine-tune the model and how to calibrate in case you have used any of these balancing methods. So that will broadly be the structure of the study and also the talk today. All right, so as I was trying to say, the first step really is to understand, is skew the real problem? And again, looking at the two data sets that we had, contrasting C with D, what we really did was to pick up all the features and do a simple scatter plot, as in the XY plot, in this case, X1, X2 plot, for each of the critical variables. So obviously there will be more features, but what we've done is just shown a snippet of this scatter plot, few of them, right? So if you see on the left-hand side, which is the C case, the cancer detection case, the reds are the positives or the cancerous records, and the grays on the chart are the healthy records, or the negatives in this case, right? So what is the idea? What we see in this graph is very clearly that there are a few attributes. If you look at, for example, ATTR3, there are a few attributes where you can very easily bunch up all the reds together, right? There is some clear pattern emerging, which may be helpful in the final model build that you do. However, if you see on the right-hand side, which is the D case, the reds are really interspersed in the grays, right? You don't see very clearly the differentiation or the pattern emerging, which sort of hints you upfront that this classification in D case is not going to be that simple, right? So the challenges a lot of times are not really in the number. In these two cases, if you look at it, the skew is same 2%. But the features that you have, the features that you've extracted or engineered are not robust enough to help you with the classification, right? So that usually is the first part of the study. And then the second step is to understand if accuracy is the right metric. See, a lot of the machine learning standard algorithms work on error minimization, right? And error usually is calculated, is 1 minus accuracy, if you will, right? So that's how accuracy is evaluated. Now, in this case, if you look at the example that we've quoted here, the NPS or the Net Promoter Score survey. Let's say an organization is running an NPS survey and there are only 10 clients to be studied. And you as a data scientist have come up with a model which is predicting all 10 of them to be promoters, right? In actuality, let's say there is only one detractor. Your accuracy for the model is 90% because you have predicted 9 out of those 10 very, very accurately, right? Pretty high accuracy. But then your model is totally useless. Why? Because there's only one detractor and you've not been able to accurately identify that one. Okay? So it's a very simple example, but helps explain the fact that accuracy as a metric fails in imbalance classification. Okay, even a naive model can give you pretty high accuracies, at least up to the IR ratio to begin with. So what do you do? Again, we've quoted a very, this is from Jason Brownlee's book, which helps you understand what metrics to use in a very heuristic fashion. Okay, so given your problem statement, what you really could resort to is understand what you want to do, right? Whether the output of the model is going to be labels for each of the classes, or is it going to be probabilities for each of the classes, right? Given that answer, you could use the sort of guidance to select the right metric. Okay, so given our experience with at least 20-25 models that we've developed in the last few months, these are the suggestions that we had, or the learnings rather. A lot of times, AUC will come to your rescue, right? AUC is one of the key metrics that could help you understand and differentiate between the paths of two models that you've developed. And as we go along, we'll try to understand AUCs better. Okay, there's another very popular metric which is called Bryoscope. Again, we'll go into a little bit more detail of Bryoscope later on. But the point is that if you're looking at probabilities, you'd rather go with the Bryoscope and AUC as the assessment metric than accuracy. And there's another metric if you're looking at just predicting class labels and you're not worried about raw probabilities, then you may want to look at G-mean, which is the geometric mean of the true weights. Okay. We'll move on. We'll try to understand what is AUC a little better now. Yeah. So the beauty of this metric AUC is that, as I was saying, this is a unified metric, right? It doesn't depend on the probability threshold, okay, which is a major fallback of metrics like recall, precision, or even F-score. Right? They need a threshold for you to be an optimal threshold. Then you calculate the classes and then you calculate the metric. However, to calculate AUC, all you need is the probabilities that the model has thrown out, right? And it also doesn't depend on a priori class probabilities, which really means that it is, and hence it performs, by the way, better than accuracy, because accuracy depends on what IR ratio you have, right? So, and hence it's a very strong metric. An intuitive way to understand AUC, because in our client conversations, we found this question coming up very, very often. What do you mean by AUC, right? What do you mean by recall? And I'm sorry to say this, but this confusion matrix is never helping, right? It just sort of confuses people even more. So what we've tried to do is just give a very basic intuitive understanding of AUC. Let's say you've developed a model, right? An imbalanced data model. The model is ready and it is giving you the probabilities. What it does is for each of the record that you try to score, it gives you probabilities. So what AUC helps you understand is likelihood of any randomly selected minority observation. If you were to select any of the positives randomly, what are the chances that your model will give you a higher score for that particular record than a majority observation? So that's a very simple way to understand. You randomly pick up a positive and see if your model is giving you a much higher probability as against any randomly picked up majority observation. So and hence the power. Now, if you ask me technically, how do you calculate? Everybody knows this, right? You Google this AUC and you get this curve, right? It is area under the curve if you were to plot the true positive rate against the false positive rate. Again, not going too much into this, not very helpful, but the point is again very simple. For a very low false positive rate, if you're able to make this curve hug the top left of the chart, you have a better model, right? You have a higher area and you got a better model. All right. What we try to do is compare, right? We began with an initial hypothesis that case C, right, cancer detection, should be slightly easier for us than case D. And obviously, that's what we see if we were to compare the initial very basic models on AUC. The basic model for the cancer detection case gives us anywhere around 8.85 to 0.95 in terms of AUC. And for the D case, we get AUC which are a little lower. I'll not say very weak model, but still not as strong as C case. Okay. Yeah.
Right. And just to add, Swati, I think the AUC also in real life examples depends a lot on the quality of data. So
Correct.
if we have really good features, if there is a very clear separation of classes, your AUC will go up.
Absolutely. Yes. No doubt about it. So we keep on falling back to our step number 1, which is evaluate your data, right? Feature selection or feature extraction become very, very key in most of the problem solving. Okay, we move on and try to understand Bryoscope a little better. So as we discussed, if you're looking at probabilities, one of the best metric to look at is Bryoscope. Why? Because it gives you a good idea of how far are your predicted probabilities from the true class indicator, right? In mathematical terms, it is just a mean square error if you were to calculate it for your predicted probabilities with respect to the actual class indicator. So y would be actually 0, 1, and pi would actually be the predicted probabilities from your model. So in essence, it's a loss score, lower the better for the model. Intuitively, again, if you were to understand it, it is a summation of the calibration of your score and the refinement of your score, right? So calibration is depicted usually with this calibration curve, where you try to plot the actual score versus the predicted score in bins, right? So if that line is closer to this diagonal, you have a very well calibrated score, right? And refinement again is if you were to bin your predicted scores from 0 to 1, how would those bins or histogram look like, right? So if you have a fairly refined, fairly strong score, what you would see is a U curve emerging here, right? You'd see a peak at 0, you'd see a peak at 1, right? And then you can say that your score is pretty refined. The resolution is high. Okay, and you would get a pretty low Bryoscope in that case. Again, we try to compare C case with D case, and as expected, the Bryoscope for C case was much lower than for D. Okay, so in summary, this is a metric which reflects the bias of your final model, the probabilities that your model is throwing. All right, we have another question, and Amit, we take a pause to see if you have any relevant question, something relevant to the topic we've covered so far.
No, nothing related to this topic, but there's one generic question which we could take up. Maybe that is data balancing always required or not? Can we directly go ahead and model, or is it necessary to do something with the data first?
Sure. Again, we have a section on balancing, so we probably take this up at that stage. Yeah. One question that we all had for you as we go through this little technical, not so technical, but a little technical talk is, have you used AUC in your experience in any of the models that you've built? And have you come across any challenges in using that as a assessment metric, right? And why do you think it didn't work? I would not say it didn't work. AUC works a lot of times, but there are times when you can't do with AUC alone, and we've encountered that many times, right? So we'd like to listen more if you've had any such experiences. All right. So now the third step, right? What we've done so far is we've evaluated our feature space. We've gotten the right features in. We've studied the problem and the skew. What we've also done is selected the metric for evaluation. Now is the core of model development. How do you evaluate various algorithms? Is the third key question facing you. Okay. Now this is very standard step. What we typically do is we have a lot of linear classifiers available. We have a lot of non-linear classifiers like decision tree, nearest neighbors, support vector machines, etc. available. Similarly, ensembles and one-class classifiers. We typically begin with running very base models for each of these, right? So select 1, 2, 3 from each of these sets and run a very basic algorithm, which we call spot checking, right? Again, a term I've borrowed from Jason Brownlee, but very, very relevant in terms of understanding, from a plethora of machine learning algorithms, what is it that would work for you, right? For the kind of data that you have. So we begin with evaluating 15, 20 of these basic algorithms and try to see what are the 3 to 5 top performers from them. No fine tuning, no balancing yet, just plain simple algorithm run, right? Spot checking. We did this for the 2 cases that we had, and here are the results. What we're showing is just for one of the algorithms selected, the best out of the lot. Right? So you could see logistic regression, for example, gave an AUC of 0.92 for C case and 0.78 for D case, and so on and so forth. Right? So what do you do after this step? We select 3 to 5 top performing algorithms, right? Not necessary that each of these blocks one has to be selected. Just select top 3 to 5 of them. More likely that you would be doing good, right? It doesn't matter if, for example, isolation forest or one class classifiers don't give you the AUCs, you don't need to pick them up, right, at this stage. So the whole idea is to select 3 to 5 top performing algorithms and move on. Okay. In our case, we've not evaluated one class classifiers. Typically, it's suggested that these be used in cases of severe skews, right? Because they suffer from one of the biggest problems, which is you have to let go of one class totally, right? So there's a huge information loss that you have to be ready for. So we've not evaluated for these cases, but they certainly stand a chance in anomaly detection or cases where you encounter very severe, maybe sub 1%. Okay. All right. So once you have selected those, 3 to 5 algorithms, the next step is to study the balancing methods, which essentially means, and this, by the way, is the core of solving imbalanced problems, right? What we need to do is somehow remove the skew, right? And there are 4 or 5 methods. I'm just trying to explain the first one, which is data-based balancing. And this is also called a pre-processing method, which essentially, just picks up the data and tries to balance it artificially. There could be multiple ways to do it: oversampling, undersampling, or both, right? And we'd cover that, in some detail later. But again, this is a pre-processing method where you change the training data itself. The second method is cost-sensitive method, which basically tries to use and modify ML algorithms. That sometimes it may be a good mix of data pre-processing itself, right? So what you try to do is attach a cost matrix to your misclassification, both the classes. A lot of times, and let me use, in fact, the next slide. Yeah. So in cost-sensitive methods, what we are saying is not all errors are equal, right? So if you wrongly predict a positive class as negative, it may not be as, of a similar cost as predicting the other way around. So you attach a cost matrix to each of your false predictions and accordingly use them either in changing the algorithm, right? You train the classifier and you modify the errors that are being optimized, which is called internal handling of the costs, or you resample it using this cost matrix, right? So you could use these costs and again create your training data in a manner which balances the whole thing. And finally, you can also use ensembles, which means you're using multiple classifiers and then using your cost matrix to select or weight them for your final prediction. Right? So that's the whole essence of cost-sensitive methods. In data balancing, as I was saying, you have three ways to go about it. You can either oversample your data. So oversampling basically focuses on your minority observations and tries to oversample them or increase them, right? You can either do it randomly, just select any random minority observation and oversample, or you could use a machine learning driven approach to do that, right? Again, it becomes complicated. You can use SMOT, which is synthetically oversampling your minority observations, but in a convex manner, meaning your new observations would always be within the area or the feature space of your old observations, right? You could do this using machine learning algorithms, maybe KNN-based SMOT or SVM-based SMOT. Right? So multiple methods, again, we could call them ensembles as well. They're all essentially combinations of either you want to oversample minority or undersample your majority observations. Right? So a lot of techniques available for undersampling as well. Very popular of them is atomic links, right? Which creates pairs of your majority and minority. And tries to look at the nearest of them and then remove the majority from those pairs. So it's a lot of techniques available to artificially balance your data before you go in for classification.
Right, Swati, before we move on, there's one question from the audience. It's coming back to one of the topics we have discussed earlier, that when we say we have a severe skew, what kind of IR values can we say that beyond this IR value, it's considered severe? So is there a benchmark? So just rephrasing that question.
Sure.
So,
yeah. So again, it's very, very difficult to answer, right? And right. I think rule of thumb, according to us, I mean, the studies that we've done is anything sub 1% is very challenging, right? You cannot just do without studying all of these methods, and you need to study one class methods in that case as well, right? So anything, I would say, if I were to put a number to it, anything sub 1% is severely skewed. In this case that we're studying here, we could manage it without one class, right? We could manage 90-95 in terms of AUCs, which is quite a good number to look at. We would not recommend one class, right? So it is totally dependent on the kind of features that you have, the kind of data that you have, and the separation that you're able to see.
Right. So to be just to rephrase it, there's no right or wrong answer to it. It depends on what kind of modeling you're trying to do. So less than 1% would typically be an IR value of 99, but I mean there can be an imbalance even lower than that value. So it depends on a case-by-case basis. There's one more question which is coming up. This goes back to the confusion matrix we had. That while modeling, do we prioritize between minimizing false positives or do we minimize false negatives? Or, I mean, how do we decide which one to focus on? This is a question from Prakash.
Okay, all right. Yeah, so again, a very tricky question. Usually the answer you would find in the subject matter expert or the domain expert. Right? So for example, in the case of production, and subject very, very close to our heart, defect detection, for example, for a defect detection case, false negatives are very, very costly, right? You don't want to call a defective product as non-defective and let it go. So false negatives become critical there. Similarly, in medical diagnosis, right? You don't want to let go as a non-cancerous case as a cancerous case. Right? There are less costly examples where false positives become very critical. So I would say the answer comes from the domain and the cost matrix. That cost matrix is very, very critical to be evaluated. You need to put a cost to your false positives and compare it to the cost of your false negatives. And therein will lie the answer.
Right, and I think this largely depends on the domain. So, for example, let's say we are talking about healthcare, then whether which is a bigger loss to us, detecting, let's say we are trying to detect cancer patients. So, is detecting a patient incorrectly as having cancer and having him undergo a lot of chemotherapy, which can have adverse health effects, is that more important to us, or is not detecting cancer in a patient and letting him not go for treatment, in which case he may even lose his life? So it is dependent on the domain, depending on the situation. So there is no right or wrong answer to this situation.
True. Yeah. All right. Unfortunately, no right answer there. As for many cases in machine learning, the answer comes from the practitioners mostly. All right. Any other relevant, pertinent question, Amit?
No, nothing as of now. I think I'll post. We have some more questions. Let's take it as we go along.
Okay. Okay, great. Yeah. So what we did very, very quickly, we tried to compare again C and D, both the cases that we have, using all these combinations, and I'm showing only a few of them here. If you really do the permutation combination, you'll see close to 100 or more of such combinations. That you have to try, and unfortunately, iteration and running all of them is very, very critical, right? You don't know where you'll see that little jump in AUC that'll help your particular study. So in this case, for example, SVM SMORT worked well for us, which essentially is running SMORT using SVM technique, right? SMORT, if you run a plain standard SMORT, all it will do is pick up all your minority classes and interpolate between all the pairs, right? Whereas an SVM SMORT will work on the boundaries. Right? It will identify the boundary of majority minority and try to give you the right samples of the minority class to be oversampled using SVM. All right, so last step in the whole model build here would be probability calibration. Again, a very, very critical step and a differentiator also for imbalanced classifications. Especially so if you're using any of the data balancing techniques or the pre-processing of training data techniques. And here's why, right? And again, I've tried to pick up from a very insightful paper, and I've quoted that here, calibrating properties with undersampling for unbalanced classification. It helps you understand and appreciate the intuition behind why calibration is needed. So one of the examples quoted in the paper are, if you were to pick up randomly both the classes, the majority and the minority, from two Gaussian distributions. What you see here in pink is a normal distribution with mean 0 and standard deviation 3, and another sampling, another distribution of normal numbers again with a mean 3 and standard deviation 3. So what you do is randomly pick 10% of your cases from this green distribution and remaining 90% from this pink distribution, so as to artificially create an imbalanced data set, right? Higher ratio 9. If you were to build a model using this data set, a very simple model will give you these probabilities, right? So what you see in pink here is the probabilities from the new model that you've created from balanced data set, right? And in green here or blue, one of the lines here, you see the actual probabilities. What you see is that if you were to use a balanced data set for model development, your probabilities will be way off from your actual probabilities, right? And this is why calibration is very, very needed if you're transforming your data and then creating a model, right? And after calibration, the P prime curve here comes to be much, much closer to the real probabilities. It's a very simple way to simulate the whole, balancing of data set, building a model, and then seeing where your probabilities are coming out to be. All right. So in summary, calibration is a must for all imbalanced data models if you've used data balancing in the beginning.
Right, Swati, one related question we have at this point, that this calibration that you mentioned, what does it basically do intuitively? What does it mean?
Right. So, so calibration. So we have to go a step back to understand the intuition behind calibration. So when you are artificially balancing, and we'll pick up again the same example here probably. This is a 10% positive data set, right? If you were to balance it and make it 50-50, you are creating a new data which is way away from the actual data that you have in practical life, right? So you would make this 50-50 artificially, and then use test data to test out your model. In the test data, the probabilities will not be 50-50. The test data is real life data. The probabilities will be 10:9, right? The ratio will be 9 again. So before you use the model probabilities, you have to calibrate. And what does calibration do? It is just, and in this case, for example, you have PS as the non-calibrated and P prime as the calibrated scores. It's just a calibration of the sample, bringing it to the scale of your a priori probability. So it's just a scaling effort, doesn't change the order of the probabilities at all. It just scales it to the a priori probabilities, right?
Right.
I think
Right.
that's it answered that
That's
question.
fine. Just a quick time check, Swati. We have another 10 minutes in this session, so let's maybe take up a few more
We
questions
are
and run through it.
okay. All right. We are almost at the end of it, so we should be doing well. So what we want to do now is this actually completes the framework that we were trying to suggest to handle such problems. We try to wrap it up with few practical challenges and experiences that we've had working on such complicated data. And this really sums up that whole set of challenges. We've tried to structure or segment these challenges on two axes, on two dimensions. Few of these challenges would actually, if you were to overcome those, you would get a good impact on your accuracy. All right. However, some of them will be very, very challenging in terms of running them, or time consumption in terms of simply coding or running various combinations. Right? So it's a good trade-off between the effort that you have to apply to overcome those challenges vis-a-vis the results or the value that it will add to your final accuracy. All right. So just want to highlight few of the impactful ones. Right. So getting more features, again, going back to the drawing board. Once you see that you don't have enough features to segment your classes, right? And a lot of times, because if you see the examples that we've quoted here, specifically case D, we did see that it'll be challenging in the beginning, right? The feature space was not as full of patterns as we would have liked it to be. So there are a few options that you have. A lot of times collecting new data is going to be costly, but feature extraction techniques, feature engineering techniques would be recommended, right? And there are a plethora of ways to do that. So getting more features would not always mean go back and collect more data, right? It would mean do better at feature engineering at times, right? Feature selection methods, very, very powerful. And I think this is one of the steps that has helped us a lot in the model building that we've done. So how are you, you may start with thousands of features. How do you select the right ones? How do you do it algorithmically, and how do you apply some really basic filters? So there's a structured way to do it if you read about the subject, right? There are basic filters, there are wrapper methods, there are embedded methods, and then there are combinations and samples. So this is very time consuming, but I think one of the most impactful ways of impacting your accuracy. All right. Selecting the optimal number of features. One of the very frequently asked questions in our client conversations is, why are you using just 10 parameters, right? Why don't you use 30, 40, 50, right? You have so many. We want to understand the effect of all. right? So using all the features is not always the right approach, right? You may have a lot of them available to begin with, but selecting the right ones will help you reduce both the bias in the model as well as the variance in the model. So very important step in the entire flow. All right. Deciding on the evaluation metric, not really deciding, but including more than AUC. And I know we began with that question of when do you think AUC didn't work for you, right? In our case specifically, we found AUC as a good metric, but there were cases where the precisions were pretty low, right? AUC is high, precision is low. You still go back to the drawing board because you want a good balance between precision and recall. Right? So include the metrics of importance, false positives, false negatives. Do that check with your business before you proceed on to model building.
Right, and just to add, Swati, in our case, the problem we were solving, although we could have the best F1 score, what our focus was more on the recall, getting more and more defects in place. So we had to prioritize the recall over getting the best F1 score, which is something which will only come with experience and what the clients demand.
Absolutely. Yeah. All right. Few not so impactful yet very important steps to be followed, which will help you develop the right model. Use of pipelines, right? Scikit-learn and both, Scikit-learn and Imbalanced learning libraries provide you with pipeline features, which sort of help you modularize the whole code and give you the ability to run it with so many combinations so easily, right? So definitely recommended for any large scale project that you pick up in this space. Choosing the right model, again, hyperparameter tuning, I think, again, a very time consuming step in the entire thing. We typically found that the impact created is not as great as the time consumed. So we ranked it a little low here. I'm sure few machine learning experts may come back and question us on this. But again, purely driven by our experience. Hyperparameter tuning, I think, with experience, you can tune a lot of it probably yourself. Okay.
Right, and one point about this cross validation as part of the pipeline, just to add here. Typically, we end up kind of doing a oversampling, undersampling, and then if you take a training and test sets, that is an incorrect approach. So because that's something called data contamination. So you have to have cross validation as part of the pipeline. So you create the n different cuts of data. You do the you kind of upsample that, and then within the pipeline you do the modeling. So it's very important not to do an upsample or downsample outside the pipeline. That's one thing to keep in mind. It's a common mistake.
Yep. So treat validation sample, if you're using CV approach, treat the validation fold as your test, right? It has to be unseen data. You can't do manipulations and you can't derive your parameters out of that. Keep it away, use the other folds for sampling as well, and any other transformations that you're doing, in fact.
Right. Swati, one question which is coming up from Naveen and a few others, it's a very interesting question on the slide, that what is the best algorithms or models for handling imbalanced data sets?
Okay.
I know there's no easy answer, but your take on it.
Yeah, you're asking all the tough questions. I thought we
Right. All subjective answers, but your take on it.
Yeah. So right algorithm, again, depends on the data that you have, right? I keep on saying that again and again, cliched answer, but study the kind of features that you have, and that will give you some way of handling it, right? If you look at the research papers, a lot of them suggest for imbalanced undersampling approaches, right? A lot of them say that oversampling doesn't work. SMOTE, for one, 10 out of 20 papers that you read will say don't use SMOTE for imbalanced data. But that doesn't stop us from using and seeing what is the impact on AUC. It's very easy. As I said, decide select the sampling method, choose the right model. All these could be a part of your pipeline, right? You can evaluate all of them. But if you go by research papers, I would say again, if somebody wants an answer to this question, maybe try undersampling all of the methods, atomic link, CNN, RENN, thousands of them. Study undersampling methods and study KNN SVM, right? Study these combinations to begin with, because a lot of papers that we've read suggest these methods, right? But our suggestion would be try all.
Right, and one thing to also to keep in mind is that don't discount the native, the basic machine learning algorithms. We have seen instances where the plain vanilla logistic regression was giving us better results than say XGBoost or deep learning models.
Right. So logistic regression beating the hell out of neural networks. That has been our experience in the last 6 months. So it totally depends on your data, and no straight answer to that. Shall we move on? One more slide left, Amit.
Yep. Let's quickly move on. Last 2 minutes left.
All right. So key learnings. Again, we've spoken through most of them. Start with a very strong descriptive. Understand the separability of your classes. If it is all interspersed, no clear boundaries, no hazy boundaries also, please go back to feature engineering. Do the right transformations, try all of them. Do the feature selection in the right way, right? Use multiple approaches, try multiple sets of features, right? So sometimes few colleagues, of ours hinted, let's just go ahead with wrapper methods. They look to be better, right? So things will be faster if you omit few of these steps, but you would never get to know what is the right model, right? So try them all. Try all combinations. Doesn't matter how much time it takes, right? Structure your code and try them all, right? Select the right metrics. These are the 3 that we've suggested. Go for AUC for ranking. If you're focusing only on predictive accuracy, both the classes, go with G-mean. And if you're worried about the bias, if you're looking at raw probabilities at the end of the exercise, please go for Bryoscope as well. Use of pipelines, I can't stress more on that. Very helpful to develop a robust production ready, I would say, code, right? And calibrate. Don't miss on calibration just because the last step your model is done. AUC is great. Right? Don't miss on calibration, because if you're using probabilities, calibration is must. Okay, I think I'm done with it. Amit, any other relevant question?
No, there are a couple of questions, Swati, but we have run out of time, and I think we have addressed the most important of all the questions. So I think we are good there in terms of time. Sorry to the participants whose questions we could not take up, but please bear with us. Thank you so much for attending this session, and thank you, Swati, for such a wonderful session.
Thanks a lot. Thanks, everyone. Back to you.
Thank you, guys.
Swati, could you come on camera on a minute for a bit, please? Yeah, there you are.
Oh, I was on the camera.
No, you were not. Now
I was not in the camera all the while, is it?
You're doing a disappearing act.
Okay.
Okay, it's excellent session, guys. Excellent session, Swati. It was as if you were in a Zen meditation camp. Spoken. I mean, you showed your mastery. The sessions were like as if I was in a Zen meditation camp. So good session, guys, and I'm sure this will. Your efforts will take us places, and proud of you, Amit, Swati.
Thanks a lot. Thanks a lot, everyone, for joining in. Thanks, Amit. Thanks, Sid.
And thank you.